All right, folks. So as we discussed before, we're talking about things like matter, thank you, matter and energy, right? So basically for matter, you should be able to identify something that is matter or not, okay? So anything that has mass and occupies space. Remember we had a conversation about like electromagnetic waves. This is not matter, okay? So matter can be divided into two large categories from, the chemical standpoint, the substances that are pure and mixtures of substances, okay? So an important difference between the two is that when you have a mixture, substances are not chemically combined. When you have a pure substance, it can be a combination of different elements, but the idea is that pure substances always have a defined composition. For instance, water is going to have a composition of 2 atoms of hydrogen and 1 atom of oxygen, no matter where you sample that water. Now, as you can see here, pure substances can be broken down into 2 large categories. One of them is elements, which list you basically can see behind you in the periodic table. And another type is compounds, which all of them consist of 2 or more elements. Mixtures, which are not, remember, substances that are not chemically combined, can be homogeneous. A good example of homogeneous mixture, they use brass, but I think much easier is sweet water. Okay, that's a homogeneous mixture. Or the mixtures can be heterogeneous. To be honest, coins at the bottom of the glass, to me, is a bit of a stretch. But let's say you go to Lake Erie during the storm and there's like dirt and sand and stuff floating in the water. That's a pretty good example of heterogeneous mixture.
Is it the same concept as oil and water?
Sure, yeah. Oil and water would be heterogeneous mixture, yes. Absolutely. So let's talk about pure substances. So what's the difference between, well, we kind of mentioned what the difference is between an element and a compound. As a reminder, any pure substance is a type of a matter with a fixed composition. The material that these bottles with a cleaner are made of, I think it's high density polyethylene. It has the same composition throughout, okay? The difference between elements and compounds, as we mentioned before, that all the elements contain just one type of atoms, okay? Like, if you will isolate oxygen, okay? Oxygen is made out of just one type of atoms, oxygen atoms. Now, compounds always consist of 2 or more, okay? Whether it's water, glucose, proteins, nucleic acids, those are all compounds and they consist of multiple types of atoms. An important thing about compounds is this. They are combined in the same proportion. Remember water that I mentioned? Glucose, no matter where easier, sucrose, sugar, table sugar. No matter where you buy it from, it's going to have 12 carbons, 22 hydrogens, and 11 oxygens in a single molecule. So elements, copper, lead, aluminum. The work that you've done last Monday with identifying the densities of materials, those were zinc, copper, and aluminum. Okay, those were elements. Okay, not just one type of material, that's not a great statement. it's one type of atoms. Compounds, I already gave you an example of sugar and water. So here's the thing. You see this combined in a definite ratio? One of the great examples here is hydrogen peroxide versus water. Both hydrogen peroxide and water consist of hydrogen and oxygen atoms. But if you combine them in the proportion 2 hydrogens to 1 oxygen, as you can see here, it's going to be water. If you combine them in the proportion 2 hydrogens and 2 oxygens, that's going to be hydrogen peroxide, a compound with drastically different properties compared to water. Right? Okay? Don't ever try to drink it.
I was just gonna ask you, it's still close to water?
Yes.
So it's like not even.
There was a story back in Mother Russia when a nurse accidentally gave a patient an enema, but it was prepared not on water, but at hydrogen peroxide. The rectum's gone. So yeah, it's a pretty aggressive chemical compound. Okay, now, compounds obviously contain elements, okay, like water contains 2 elements. Sodium chloride contains elements sodium and chloride, right? And you technically can break sodium chloride down back to individual elements. Okay, it's not cheap and super energy inefficient, but you can do that. Okay, one important thing that I'm probably gonna run ahead of a train, okay, and tell you something. I'm not gonna put it on a slide, but sodium is an extremely reactive metal, which if you drop it in the water, let's say you drop it in a toilet, it will explode and literally break down the toilet if the chunk is large enough. Chlorine gas is a very strong poison which was used by Germans to poison French troops in 1915. When you combine them, you get table salt. The point is, chemical properties of a compound are different from individual chemical properties of the elements that this compound is made of. Making sense? Questions on compounds and elements? Okay, let's talk about mixtures. So, 2 or more substances that are physically mixed. What does that mean? It means that you can separate them using physical but not chemical methods. Okay? Does that make sense to you? Like, you cannot separate hydrogen and oxygen and water by physical methods like evaporation or crystallization or filtration, stuff like that. So, mixtures can be different. They can be homogeneous, they can be heterogeneous. Let's say you have a homogeneous mixture here. Let's say it's a solution of dyes in, I don't know, alcohol, okay? It's a homogeneous mixture. You don't see individual beads of dyes, and if you leave it for, let's say, 2 years and come back 2 years afterwards, you're not going to see it separated. There is no separation over time in a homogeneous mixture, but you can separate the individual components by, for instance, running it through chromatography paper. The capillary effect will bring all the chemicals up. And let me ask you this, which kids are going to easier get stuck between the trees, the really fat and chubby kids or scrawny kids? Fat and chubby, so the larger molecules will move slower and the smaller molecules will move faster. Sounds fair? Now, if you have a heterogeneous mixture, let's say sand and water, you can filter it. Okay? That's one of the ways. It's not the only one. So, homogeneous mixture, in terms of its composition, it does consist of two or more substances, but the composition is uniform throughout the sample. A good example of this, again, air. Air is a mixture, right? We have 79% nitrogen, 20+% oxygen, and small bits of water vapors and carbon dioxide. Am I making sense? But if you sample air here or in Cleveland or, I don't know, in Europe, the composition, I'm not including the pollution, but the composition will be the same. Okay? So here an example is a brass. Any alloy is a homogeneous mixture. Steel is a homogeneous mixture. And this is an example of breathing mixtures for scuba diving. Okay, for a variety of physics reasons. Air is suitable for breathing only down roughly like 30 feet. Then you have to have special mixtures of various gases. Any questions? I think it's pretty straightforward. Okay, heterogeneous mixture, obviously composition varies between different parts. For some reason, I really don't like that example of water and copper, but if you take a sample of Lake Erie water and try to identify the amount of solids, it's going to be different depending on where you're sampling it. Okay? So which of this is a pure substance? Tell me, please. Helium. Aluminum foil. That's it. That's it. Those are mixtures. Okay? Well, since we are so awesome, I'm going to just skip this check. Move on to this. Homogeneous or heterogeneous? Let's start with hot fudge sundae. That's heterogeneous because it will separate over time. Baby shampoo. This one should be homogeneous. Sugar water. Homogeneous because, let me explain what, and this is heterogeneous obviously. Let me explain the principle. Okay, if you take what, second? Because, here's the idea. You take a mixture, you live it. Not for a day, for 2 years. In the ideal case scenario, absolutely sealed container, no contamination or whatever. You leave this sugar water or baby shampoo there, they're going to just be there. Nothing's going to change them. You leave hot fudge sundae, it's going to eventually separate. One of my favorite examples, milk. Homogeneous or heterogeneous? Heterogeneous. Huh?
Want to separate?
Yeah. If you buy like a really proper milk and leave it in the fridge, eventually, no. I'm saying ideal case scenario, it doesn't get spoiled. Fat that's in milk eventually will flow to the top. But yeah, it's going to happen. If you buy grocery store milk, which is homogenized, it's going to get spoiled before you can see that because the fat is really well homogenized. It's very small droplets.
So would milk be homogeneous until it separates, or is it's just automatically, it's always considered heavy?
Even if it takes a year, it's heterogeneous mixture. This is why I don't like the coins and the water example, because it lacks subtlety. And we're all about subtlety, to be honest. Okay? Does that make sense? Like coffee. That's a heterogeneous mixture, but it's going to take a while for solids to separate. I'm talking about filtered through. Yeah, there are going to be some solids that will get through filter. Make sense? Yeah. Now, states of matter, folks, it's just like normal experience, right? So solids, definite shape and volume, okay? Liquid, only definite volume. As all you know, you probably saw this very, very old meme that cat is a liquid because they will accept the shape of a container, all right? And then gas, not only will it have the shape of a container, it doesn't have defined, it has a volume of a container. Making sense? Yes, no? Okay, so think of it this way. Imagine I give you a very, very tiny balloon and you exhale into that balloon. It's going to be inflated to a certain volume, right? Which is limited by the balloon. Then you're going to exhale into a much bigger balloon. It's not going to have that same volume, right? You can take this air that occupies that room and basically pressurize it into a little tank. You can do that. So the volume for a gas isn't defined just as the shape isn't, okay? Good? Understand the arrangements. Obviously, when you move from solid to gas, the arrangement becomes random, but in liquids, the random arrangement, the particles, whether those are molecules or atoms, are still pretty close. And interaction, therefore. So solids, the interaction between the particles is strong, and it's usually a chemical bond. Well, in liquids, it's not as strong, and in gases, it's the weakest. Okay? Also, we do acknowledge that molecules of, say, water or atoms of a gas, they constantly move. But even atoms and molecules that comprise a solid substance, they also move, albeit very, very slow. Any questions on different characteristics? All good? Okay. So as we discussed before, the temperature, so it's, measure of how hot or cold an object is. But you should start thinking about the temperature as the measurement of the heat energy that a body, an object, possesses. Right? Make sense? Because think of it this way. Like if you have a super hot piece of metal and you throw it in a bucket of water, some water will evaporate because that piece of metal will give off heat, give off energy to the bucket of water. Now, yes, it is measured by thermometer. Celsius or Kelvin, depending on what scientific application you use. If you need to establish what is the temperature, Celsius is much more convenient. If you talk about the temperature difference, it doesn't matter. Remember, the difference between boiling and freezing points for water are 100 degrees Celsius or 100 Kelvin, so there's no difference. The only temperature scale, and I'm sorry, I know, that makes no sense is the Fahrenheit, because the reference point's just absurd, okay? So you can see the alignment of this reference points here. We talked about them last Wednesday, right? Cool. So the conversion. So these are the formulas that I believe you're going to have on the handout, but I will check at the end of the class. This is how you convert, let's say, from Celsius to Fahrenheit. Okay? This is a pretty straightforward formula. Okay? If you want to go back, okay, this is your formula for Celsius. Fahrenheit minus 32 divided by 1.8. Okay? Does that make sense? Now, what I'm going to tell you now isn't stuff that will be explicitly asked in the exam, but you will be converting Celsius to Fahrenheit or vice versa. Okay? I'm going to give you some useful stuff. Hear me out. So obviously 0 degrees Celsius is 32 degrees Fahrenheit, right? And you know that 100 degrees Celsius is 212 Fahrenheit. Okay? I mean, that was on the previous slide. But here's the thing. When you convert and you want to double check if your result makes sense, there are few very easy reference points that are super easy to memorize. So 82 Fahrenheit is 28 Celsius. 61. Do you see what I did here? I flipped the numbers. 61 Fahrenheit is 16 Celsius. And negative 40 Fahrenheit is negative 40 Celsius.
Basically for 80 Fahrenheit is Celsius backwards.
No, not always, no. So these are two instances when you take Fahrenheit, flip it and get Celsius. But those are only two instances like this. Does that make sense? Okay? So, 21 degrees Celsius, right? What's the temperature in Fahrenheit? So what do? You can see the formula on the screen. So you take 21 Celsius, okay? You multiply it by 1.8 and add 32. I'm going to tell it's going to be about 70. 69.8 Fahrenheit. Okay. All right. So this is an example that you may want to explore. Now, we did convert Celsius into Fahrenheit, right? What about converting Fahrenheit into Celsius? So let's say you have 102 degrees Fahrenheit. So what do you have to do? You have to subtract 32 divided by 1.8. Am I making sense? And it's going to give you like 38.9 or 38.8, something like this. I don't know, 8, 9?
38.8 or 38.9 if you round.
Yeah. Okay. So expect those problems, well, these type of problems on the exam for sure. Kelvin, so we're not going to do question.
Can you go back real quick?
I absolutely can. Go on.
Thank you.
Yes. That's what you should do if you need some extra time. So while Kaylee's finishing up, it's not. So when do we use Kelvin? We use Kelvin when we calculate temperatures using some laws of physics. They have to use an absolute scale. So for instance, when we're going to talk about gases, we're going to use Kelvin instead of Celsius. Okay? So, I mean, this is the lowest possible temperature. Strictly speaking is negative 273.15, but I'm not that pedantic, okay? There is no, laws of the universe show that nothing can be colder than that, period, okay? So there are no negative Kelvin. So no degree symbol, okay, and 1 Kelvin is 1 degree Celsius. So here's the thing, 30 7 Celsius, but in kelvins. What do? Right, you take 273 and add 37 Celsius. What do you get? 310.
Could you explain that again?
Yeah. So, okay. I'm actually going to draw something. Who was asking? Okay. Yeah. Look at this. No, I didn't want that. Okay. So these are two scales. They are, sorry, no pun intended, not up to scale. But, so this is 0 Kelvin. Make sense? And this is 273 Kelvin. And this is 373 Kelvin. Over? Good? Now, on the Celsius scale, this is 0 Celsius. This is when water freezes. On the Celsius scale, this is 100 degrees Celsius. This is when water boils at the sea level, okay? Good? So first of all, what is the difference, numerical difference, between 273 and 373? 100. What is the difference between 0 and 100? 100. So over, first of all, does that make sense that each step in that ladder, each step in the scale, Kelvin, is equivalent to a step in a Celsius scale? Yes. Now, you can see that if 273 Kelvin is equivalent to 0 Celsius, then 0 Kelvin, like this distance right here, is 273 steps. Do you agree with me? Perfect. Which means this distance is also 273, but we count 273 to the left of the 0 into the negative realm, right? So this is negative 273 degrees Celsius. Good? Make sense, everybody? Any questions before we move on? All right. So, what do we do here? How do we convert Fahrenheit into Celsius? Remember? What we need to do, and this is the beauty of it, the formula works for positive, negative, doesn't matter. So we take this, minus 15 Fahrenheit, right? We subtract 32, and we divide it by 1.8. Okay?
Negative 26.
Exactly. There are, like, since I was born and raised with metric system and Celsius scale, I still convert Fahrenheit, and I found a bunch of ways that I can talk about if you want to after the class. It's just easy. But yeah, there are some ways. Okay, so this is what happens when people who are chemists start to write about biology and medicine. They get it all wrong. Thankfully, it's not for the exam. I'm just telling you that, no. Just no. There are multiple examples in case studies from emergency departments when people arrive with a body temperature of 46 degrees Celsius. They are not lucid, don't get me wrong, but they survive. Okay? Heat stroke definitely doesn't occur up to 42. There should be several combinations of factors. So but hyperthermia is technically anything above 38 degrees Celsius. Okay? Okay, this is not, no. Normal temperature range for the human body is this. This is a medical fact. 38 and plus, you're hyperthermic. Okay, just FYI. No. Yeah. So fever and hyperthermia are actually synonyms. Hypothermia, yeah, this. Below 35.5, technically speaking. A little tidbit, just an interesting fact. What is worse from the personal perception standpoint? Hyper or hypothermia?
Which one's worse?
Which one? Like if you would ask me, what would I have? Much more preferably, what do you think I would choose?
Hypothermia?
Of course, it's a sweet relief of death. Basically, it's the least painful death known to humans is to freeze. Okay? Which one is easier to bring a person from back alive? Come on, Kaylee. I mean, it's even if you say it and it's not, I'm giving you,
Hyperthermia?
the opposite. If a person has a really high fever and you don't know the underlying cause, it's going to kill a person pretty quick. Okay? There's an expression among emergency medical technicians: the person is not dead until they warm and dead. Okay? Warm and dead. Yeah, there was a case of a woman here in Cleveland area who froze to the ground. So the EMTs were shoveling her off. And her body temperature was 20 Fahrenheit. She was brought in, she was warmed up, perfectly fine. Yeah. Huh? Yeah, it's human body is more like you can freeze to death, but it's going to take a while. Like to absolutely unrecoverable death. So 34.8 degrees Celsius, what is it in Fahrenheit? Remember what we do. We take 34.8, multiply it by 1.8, and add 32, okay? 4.8, 86, it's going to be like 95, 94 ish. $90.
$94.64.
94.64. Yep. That sounds right. Okay, questions on the temperature. You should be able to convert Fahrenheit, Celsius, Kelvin. Ability to do work, that's energy. Okay. And two main categories, kinetic and potential. Okay. Kinetic, obviously, the motion, potential energy determined by the position. So here's an example. My brother almost killed me when I was like 10 and we had started physics in school, explaining me the difference because I could not process potential energy. So here's the idea. If you have water behind the dam, it just sits there, right? Like it just sits behind the dam, okay? But it has a potential to do some work. So when you open the dam, the work can be, I don't know, destroying all the homes in its path, that would be work, or rotating a turbine in the hydroelectric power plant, and the energy of the movement of that turbine can be converted into an electric energy, right? So basically, it's potential energy, potential to do work. Kinetic energy, energy of movement. For instance, the energy of chemical bonds is a potential energy. When you put gas into your, in a car, and gas burns in a car, it moves the parts of the car so it now, you can drive it. So you convert potential energy of chemical bonds into the kinetic energy of the car movement. Make sense? Units. Joule. It's a pretty small unit. Okay? Kilojoule is 1,000 joules. So when we talk about heat, joules and calories are the units of any energy, but we're focusing on the heat energy right now. So energy associated with the motion of particles. The good example why, think about water. If you will leave cold water in like a pot or whatever, it's going to take a while for it to evaporate. It evaporates because particles, molecules, they fly away from the surface. If you put that pot in the stove, it's going to evaporate much faster because those particles fly much faster because they receive some heat. So, I don't want to focus on this. It's just something that is really cool is this. Okay? So, the amount of energy that reaches the surface of the Earth in 1 second is just 1,000 less than the entire consumption of the US in a year. So technically, if we can harness it, it's really like it costs nothing to generate, and it's the cleanest energy you can think of. Okay. Okay. This is more relevant. You will see why joule is a relatively small unit. So what is a calorie? And there's gonna get some complications, okay? But don't worry, we're gonna cover it all. So calorie is the energy that you need to heat 1 gram of water by 1 degree Celsius. 1 teaspoon contains 5 grams of water. So if you want to kind of process the size, you need 5 calories of energy to elevate the temperature of a teaspoon by just 1 degree Celsius, okay? That makes sense to you? Yes or no? Okay, so you can see it's a pretty small unit. Now, 1 kilocalorie obviously is 1,000 calories, and we can get back to this again. So, this is another example of working on conversion factors, okay? So you need to go from joules to calories. Remember, from on the bottom to on the top? So unit-wise, what should be on the bottom? Joules. What should be on top? Okay. Now you go back here and you see, oh, okay. So 1 calorie is 4.184 joules. Sounds reasonable? Now, you don't really have to do any calculations, just approximately. This amounts to 36 calories. Okay?
Can you do that one more time?
Sure. So the conversion factors for joules versus calories are these two. Make sense? Now, remember the rule. I'm going to remind you again. 2 at the top, from at the bottom. So you go from joules to calories. So you put 4.184 joules at the bottom. And you put 1 calorie on top, which means 1 calorie contains 4.184 joules. And you do the math. There will be problems like this on the exam.
So doing that equation, you're always gonna put that 4.8, because that's what the, whatever, one more slide, sorry.
Mm-hmm.
That one right there?
Yeah.
Okay,
That's exactly what I did.
okay, all right.
Compare this one and this one. You see? They're identical. I just use an appropriate conversion factor. Okay, yeah, well, I don't know what to tell you. Yes. Carbs, first you burn carbs, and you burn fats, and you burn proteins. And so here's the confusion, folks, and you need to know that. If you would look at, this unit, you see they are all lowercase. CAL. Don't look at me like I'm saying something dumb. Well, I am saying something dumb, but it's kind of, So all of them are lowercase, right? Do you see that C is an uppercase? So calorie with an uppercase C, or a large calorie, or nutritional calorie, is actually 1,000 regular calories. Am I making sense? So when you look at crackers, and it tells you calories, you see? Do you see the word calories? It starts with a capital C. It's 1,000 normal regular calories, and it shows you in kilojoules as well, which is 500 in this case. Am I making sense?
So on a test, if we were to have a capital, we lose points for that?
Absolutely. If you, on the test, if you have a question, say, how many, many calories into big nutritional calories, would it tell me 2,000, right? Because one nutritional calorie is 1,000 regular calories, therefore 2 nutritional calories is 2,000 regular calories. Clear? Good? Cool, okay.
So like in those snack crackers, there'd be like 130,000 small c
Uh-huh.
calories.
Yep. Actually, good point. 130,000 regular calories. Because it's 130 nutritional ones. Okay, so this is actually what you're going to be doing. This. Next Monday. Not exactly like this. We're going to have different God, it's not thermostat. Eventually, this word will come back to me. Okay? So basically, your contraption is going to be slightly different, but this is how energy values of food are measured. It is literally burned in oxygen, whether it's steak or snack crackers. Okay? Calorimeter. This is the word I absolutely blanked on. Yes, calorimeter. Okay. Food energy values. I don't remember if it's in the handout. I will check at the end of the class. It's pretty straightforward. You can see that carbs and proteins have the same energy value, 4 nutritional calories per gram. Fats have 9. So, and yeah, you can basically convert. Go ahead.
On a test, would we get those?
Dude, I will tell you. Like, seriously, this is the piece of information that bears no significance for you to memorize it for the rest of your life. You can look it up. As long as you can, it is more important to be able, if I tell you, hey, I have 100 grams of sugar, how many nutritional calories can I get out of them? And you go back and you look at this table and tell me, well, if 1 gram is 4, then 100 grams is 400. I find this way more important than memorizing random facts. Again, please enjoy, obviously, how we calculate. We know the amount of carbs, fat, and protein, so you can calculate it. Okay? I'm not going to go over every line in this table. Am I making sense? Good? Okay. So, this, how you solve it? You solve it by remembering third grade and rules of multiplication, right? So, 12 grams of carbs multiplied by 4, right? 9 grams of fat multiplied by 9. And 9 grams of protein multiplied by 4. Okay? So 48, 36, 84, 81, should be 165 nutritional calories. Okay? Make sense? Yeah, you should be able to do that. You actually will be doing that exact calculation on Monday, because we're gonna burn some food. Okay. Questions before we transition into specific? Good. Say again? Oh, okay.
Oh, never mind.
Sorry. Here. See? Got it? Cool. Okay, specific heat. Know the definition here. Amount of heat that you need to raise temperature of 1 gram of substance by 1 Celsius. Okay? Does that make sense? So we can write it down.
Wasn't that the same definition as the calorie, the regular calorie?
I'm going to show you the difference. So if you go to a calorie definition, hold on. We're talking about water. 1 calorie is a specific heat of water. You're absolutely correct. But specific heat is more broad term because it's just, a substance. So as we mentioned before, you're correct, like 1 calorie is the amount of heat that you need to increase the temperature of 1 gram of water by 1 degree Celsius. Okay? If you express it in joules, you just replace calories with joules. Okay? So this is something I want to highlight. So specific heat of water (1 calorie per gram Celsius) or 4.184 joules per gram Celsius. Okay? So your kitchenware, like the stuff that you cook food in, like there's metal skillets and things, right? If you put it on a stove and it's like not some fancy skillet, but it's a regular one and it's super hot, will it get hot pretty quick? The skillet, yeah? So the reason for this is this. Let's say it's iron, okay, just for simplicity, right? You can see that you need 1/10 pretty much of the heat to increase the temperature of 1 gram of iron by 1 degree Celsius compared to water. Do you see where I'm going with this? If you the lower the specific heat, the faster whatever gets heated up. Am I making sense? I don't know how big a good sauna is among you folks, but in Russia it's pretty big. And it is known when you enter like really good sauna, you take all the jewelry off. Because this gold and silver, they're going to burn you. Because they're going to get hot super quick. Okay? And the greater the specific heat, the longer it takes. Okay? Does that make sense? Okay, good. So you will have to convert, you will have to solve some problems. Remind me, at the end of this unit, we're going to go through some problems that don't provide us. Okay, I'm going to explain what conversions you will have to make. So this is an example of, why coastal towns have much milder climates than continental ones. Okay, so I can give you an example. One city in Russia, it is at, like, Cleveland is pretty much at the same latitude, but that city is on the coast of a Black Sea. They rarely see snow, and the summers are pretty mild. It's pretty much subtropics. You see what I'm saying? In Cleveland, yeah, just step out. Yes. Or in the summer, it's going to be what? It's going to be like good 90 plus, right? It's not going to be mild by any means. Another good example of the influence of water on the coastal towns is San Francisco. They have cold stream going through the ocean, right? San Francisco Bay is pretty cold. So in the summer, it absorbs heat, making summers in San Francisco pretty cool. And in the winter, it gives the heat away, making winters in San Francisco pretty nice and mild as well. Okay? So, and all of this is because water has it has the highest specific heat among all known liquids at the room temperature. Okay? Good? So, when ocean water cools, the surrounding air warms because it gives off the heat. Make sense? And if you go in the desert, well, I've never been, I really want to, but it is known that even in like early summer or late spring, it can get freakishly hot during the day. But then it gets really, really cold during the night. Why? Because sand has a low specific heat. It can be easily heated up, but then it loses heat very quickly, doesn't store a lot of it. Okay? Okay, so these are calculations. So think about it this way. What is the specific heat? It's the amount of heat energy that you need to increase the temperature of 1 gram of a substance by 1 Celsius, right? Let's say you have 100 grams and you need to increase it by 25 Celsius, okay? Good? And let's say this substance is water, so we have 1 calorie per gram Celsius. How do you know that your calculations are correct? I'm asking you, it's not a rhetorical question. What do you need to check for? You need to check if units make sense. So if you look at this calculation that I have on top of the example, can we cross out degrees Celsius? Yes, because, they are in the numerator and in the denominator. What about grams? Can you do that? Yes, we can. So now we need to find heat. Our units are calories. Perfect. Does that make sense to everybody? Go on.
Is there a double unit
All right.
where it's grams and Celsius?
Yes,
No, no.
because it means 1 calorie, hear me out, per 1 gram to increase the temperature per 1 Celsius. This is why it's 2. You can think of it as grams multiplied by Celsius.
You just don't put the 1 in front of the G.
Say it one more time.
You just don't put the 1 in front of the G, basically?
Yeah,
Okay.
yeah. So, thank you, Kalia. So you can write it this way, Aubrey. 1 calorie per 1 gram, 1 Celsius. But we just don't write ones because it's always, for a specific heat, it's always 1 gram and 1 Celsius. So we just ignore. Okay, so how much energy do we need to heat 255 grams of copper from 24 to 185? So heat, right, equals mass multiplied by the temperature difference, right? Do you follow? Multiplied by the specific heat. So what's the mass? 55 grams. So the difference, it's 185 minus 24. Everybody follows me? Good? And whatever. So we use, what do you mean, joules or calories? Do you remember? Joules, okay. So, where's the copper? Okay, copper is 0.385, okay. Five joules gram Celsius. You see, when I write these numbers, I always put units because I'm going to check, okay? Now, whatever the answer is, here's so couple of points of confusion that you guys are going to have, like you can face. Point number one, see kilojoules. Zach, what is the number? Because I have no idea.
I got 15,806, or I mean 15,806.
Okay. So this is joules, right? That make sense? Your answer should be in kilojoules. So how do you go? You have to go from joules to kilojoules, right? How many joules in 1 kilojoule? Kilo. 1,000. You need to remember those prefixes, folks. 1,000. So now you do the math and you get 15.806 kilojoules. So this is one sort of catch, the trap that you can get into. You find the answer in joules instead of kilojoules, or kilojoules instead of joules, you know. Second trap that people fall into, simply calories versus joules. So when you read a question and it asks you the answer in calories, it may contain the answer that you will get to using your, calculations, but if you accidentally replace calories with joules, it may have this answer as wrong one, and it is wrong. You see what I'm saying? So please be mindful about that. Okay, dude, like seriously, we adults going to talk about what melting and freezing is. Can we just acknowledge that this is what happens? You go from solid to liquid. You have to understand though what, if you want to melt someone, you need to invest energy. If something is freezing, you need to take the energy away, right? Obviously, they're reversible. Evaporation, boiling, condensation. So evaporation is the opposite of condensation. Everybody agrees? Okay, cool. So basically, when you go from solid to liquid, you melt. When you go from liquid to gas, you evaporate. Evaporation occurs not only at the boiling point, as you know, but it is the fastest at the boiling point. I can prove my words by just putting a glass of water and waiting for a month. Eventually it's going to be gone, right? Condensation is the opposite of evaporation. This is when, heat is being taken out. And any questions about this? Okay. So here's what we're gonna do.